So the goal of these sections are to really think about the molecular scale interactions that give rise to these sort of observations that we make in the rate of chemical reactions. So we call it collision theory. So how do we think about collision theory and things like physical state, temperature, concentration, and how they relate to the reaction rate? We think about this new idea called activation energy and transition state when molecules collide. And then there is an algebraic expression called the Arrhenius Equation that we can use to relate things like temperature to the rate constants that we've been dealing with so far. So collision theory is really the point at which we start to zoom into the molecular scale, and it's really a simple premise. For something to react, they have to directly collide with each other. That's the idea, and there's really three general tenets of collision theory. One, that the reaction rate is proportional to the number of collisions per amount of time. That should feel pretty intuitive. If you have a bunch of marbles bouncing into each other, the more often they can bounce off of each other, the higher the chance they're actually going to react. Just because something runs into it doesn't mean it will react. And so that brings in the second tenet, which is the reacting species must collide in an orientation that allows contact between the atoms so it will become bonded together in the product. This is really important if you have big complex molecules. Even for small ones, the example that I have down here is carbon monoxide reacting with oxygen gas. This is one of the steps in a pretty common reaction of carbon monoxide and oxygen. So the first step is actually shown in two different orientations. So you can see that carbon monoxide, if the oxygen collides with the oxygen atom over here, we don't really get a reaction, even if they collide with enough force. Instead, we need the carbon monoxide to be oriented such that the carbon atom is the one that collides with the oxygen molecule, and that's because the new bond that forms is between carbon and oxygen, and so it makes sense that that atom is the one that does the collide. And the last one is a little more abstract, but also maybe a little intuitive, that the collision must have enough energy when they collide that the valence shells, the things that the electrons are housed within, can actually have some interpenetration and some energy for them to start to be covalently shared with each other. So these are the basic premises of collision theory. What's nice about this is it also fits with these general rate law models that we talked about before, which shows that as you increase the concentration of a reactant, you get a faster rate. And that should be intuitive within these collision theory tenets, because if the reaction rate is proportional to collisions per time, if you just toss more of that thing in there, you're going to get more collisions per unit time. So it fits well with that sort of macroscopic model. The last quick point that I want to make is that anytime you have the collision of two molecules in space, what happens before you form the product is you form this high energy sort of pseudo-existent molecule where they're both combined together before they form the new state. We call that the transition state, and this is so short-lived. We're talking about less than a nanosecond that it's almost impossible to observe using experimental methods. There are some really fast techniques where you can see this, but generally we know this to be true, but it's very difficult to observe. So we have the reactants and the products, but we actually have this thing in the middle called the transition state, which will be relevant when we get to the next section talking about the relationship between temperature and the reaction rate. So we often use this graphical representation called a reaction diagram to really illustrate the change in energy of a molecule or molecules that are in that elementary step of the reaction. And so you have an axis that's energy here, and we have what's called the extent of reaction. You can kind of think about this like a time axis, where here is the reactants, and on the right side you have the products. In the middle you see this familiar term, the transition state. And so what's interesting is if we have this reaction that in this case is a really sort of simple idea of, or the generic idea of A plus B makes C plus D as the products. We have A and B over here. This is the energy of these two reactants when they haven't been mixed. That's their intrinsic bond energy. And when they collide with each other, they create this higher energy transition state geometry, which I said is really fleeting. It doesn't exist for very long, but it's pretty unstable, which is why it's increasing in energy. And then we have that decrease down here. So there's a couple really important concepts here that we want to take away. In chemistry so far, we have largely not considered this hump here. Really, we haven't at all. What we've thought about is this idea of an enthalpy change, or the difference in enthalpy, or delta H, between the bond energies of the reactants and the bond energies of the products. And so if I were to sort of redraw this, what we would see is something familiar maybe to Chem 107, which is we have a starting point and an ending point, and if the ending point is lower than the starting point, then we said that has a negative delta H, and that is something that the universe likes, right? You want to end up in a lower energy conformation. What we're doing here now is actually adding a little bit more nuance. Once we start to understand kinetics, we know that it's not just the difference in the original and the final states that's important. It's also important to consider the fact that there's this increase in energy before you can get the decrease. We call that bit of energy right there, and it's indicated by this EA here, we call that the activation energy. And it's a pretty self-explanatory term. It's the energy that's required when these molecules collide, A and B, to get over that high energy transition state. Once the molecule ends up here, the rest of it is downhill. So the molecule can sort of go up this whole thing, and at some point gets up here, and then it can traverse back down. Overall, we still only have this net change in delta H, right? Because the starting point is here and the ending point is here, but it's important to realize that we need these A and B molecules to collide. Their kinetic energies must have enough energy to overcome that activation barrier, or that activation energy. So as promised, I mentioned I would describe a relationship that relates the parameters we're familiar with, like the rate constant K, with the parameters of this new idea, the activation energy, or E sub A, and temperature. We call that the Arrhenius Equation, and it looks like this. So K is the K you're used to. That's the rate constant. So rate constant down here. EA is your activation energy. R is the gas constant that you might be familiar with in the gas laws chapters, PV equals nRT. That's the same R, and that of course is the temperature of the reaction. A is this sort of weird thing that we call the frequency factor, and that is a constant that essentially captures the number of collisions per unit time that we said were useful in having faster reaction rates. You can sort of think about it as how many times does your A and B molecule here make an attempt to overcome that activation barrier. That's the frequency. How fast are they doing that? Are they doing that once every second? Are they doing it once every microsecond? That's what we're talking about here. So that is the Arrhenius equation. And if I forgot to mention, the E here is Euler's E, so that is the exponent E that we're used to using in algebra. So it's convenient to sometimes write the Arrhenius equation in its natural log form. So since this is Euler's E, the exponent E, then we can take natural logs of both sides of this and get rid of that exponent. And so you get a form of the equation that looks like this. I'm not going to show you that you should be able to do that algebra, so make sure you pause the video, work that out. The reason why this is beneficial is if you look at this, the consistent theme in this class is that this is written in a linearized form, which is the same as saying that we could say that this is in the form of y equals mx plus b, which is how we would go about experimentally determining what the activation energy, this term, is for a particular reaction. So think about that, pause the video, see if you can figure out what would you measure if you wanted to make a graph in the form of y equals mx plus b using this linearized version of the Arrhenius equation, what would you actually measure and plot to be able to determine EA, and what is already known in this equation? Okay, so if this is the y-axis, then that means we would be shooting to ideally make a plot that is the natural log of k on the y-axis. That means, what do we need to measure? Well, we need to measure the rate constant. So that means measuring the rate constant. And what are we plotting in the x-axis? Well, that's this 1 over t variable here, so we can plot 1 over temperature. So that means we would need some data that is the rate constant and t, and we need, ideally, 3 points to make an actual line or more. So we would have a table of data like this. We would then convert this to natural log, and we would do 1 over in Excel, and we would be able to make a plot. That plot then should have sort of this downward looking slope. And what is the slope? Well, the slope here, m, is equal to minus EA over R. R is a constant, so if we have the slope, then we can solve for the activation energy, which is a very nice thing. And we can also, wherever this intersects our y-intercept, that's going to be equal to natural log of A, which gets at this frequency factor if we were desiring that as well. So how do we measure K? Well, hopefully that jogs some memories of what we've just been covering. So that would require you first to make a measurement of the concentration of whatever that species is that you're interested in. Let's just say we're talking about the decomposition of ozone again. So that would require you to make some measurements of the concentration of whatever that reactant is as a function of time. And with that data, then you can go ahead and see what the order is by making a plot. So you figure out the order, and there's a nice video that shows you how to determine whether it's 0, first or second order. And from the fit that you do in Excel, you can determine what K is. And of course, measuring temperature experimentally is easy. You can do that with a thermometer. And so the sequence of being able to do sort of a full kinetic characterization of a reaction here would be to start by just simply recording how much of the reactant you have versus time, and then figuring out its order. From the order and the graph of that order, you get K, and then you can do natural log K and 1 over T. And as long as you've got 3 points here, you can make that plot and you can figure out what the activation energy is. So there's lots going on here, but they sort of all build and scaffold on each other nicely. So the final thing that I want to just really super clarify here is that the whole point of the Arrhenius equation is to relate the rate constant, how fast that reaction is going to actually intrinsically run, with this new idea of activation energy, how high that barrier is, and temperature. And what is the explicit relationship of temperature? Well, you could sort of figure that out if you just sort of plug some numbers in for T and saw what happened to K, and that would develop some intuition. The whole idea here is that temperature is just a measure of the kinetic energy of the molecules in a space. That's all a thermometer is measuring. And if the whole idea is that the more kinetic energy the two reactants have, the greater propensity they have to exceed that transition state energy or that activation barrier, then as you increase temperature, you're increasing the chance of that happening, which means you're also increasing K. And you're doing that in an exponential way. So as T increases, the rate of that particular rate constant is also going to increase exponentially.